Alright, let's move on to example 3 here. So find the Thevenin's and Norton's equivalent circuit across terminal A and B. Terminals are labeled here, and by reading the problem carefully, you should be aware that in this particular example, there is not part B circuit. So only part A present. So we just work on it. So if this is clear, then next you need to recall the previous procedure here. So in this circuit, it belongs to case 2. No independent source, only dependent source. So first thing is VTH is 0. No VTH at all. We only need to find RTH. So how to find RTH? It is adding a independent source, VT, and then find the resulted IT. And the ratio between them equals to RTH. With all of these being said, here is the original circuit, and as we said, we need to add a V-test. Here, feel free to add a V-test with a particular voltage value, 1 volt, or any volts value, it doesn't matter. So this is the circuit we are going to work on, and then find the IT so that we can find RTH. IT is the introduced current due to this added 1 volt test voltage source. Okay, be careful the current direction. Okay, is leaving the positive terminal of VT. Yeah, very important. And how to find this IT? Again, no more wasting time. Just step into the KCLs or KVLs. Okay, so here I'm applying nodal analysis by choosing 2 nodes up here with node voltage V1 here and 1 volt here. So yes, the node voltage at this node is equals to 1 volt. By realizing this, I can save a lot of time. Okay. So at node 1 here, KCLs include 3 currents with these assumed current directions. Here is the corresponding KCL. So first, this current towards left through 2 kilo is equals to V1 minus voltage at this node, and then divide by 2K, Ohm's law. However, what is the voltage at this node? By reading the circuit, this node voltage is from itself towards the ground. And be careful, this is a dependent voltage source. The labeled value, no matter what it is in terms of, it is a voltage value. So the voltage at this node is nothing but 2kIx. So V1 minus 2kIx divided by 2k equals to the current here towards left, leaving the node 1. Next, the downward current here, leaving the node as well. V1 minus 0 divided by 1k. Last current here towards right, leaving the node. So V1 minus 1 volt divided by 3 kilo. Sum them all up equals to 0. So KCL at node 1. And then KCL at node 2 here, or say KCL at 1 volt here. We have these currents already been defined here in previous equation into the node, plus another current going into the node, which is nothing but IT itself, equals to the current leaving it, equals to 1 volt minus the ground 0 divided by 2 kilo. KCL at node 1 volt. And you can count, we have V1, Ix, IT, 3 unknowns and 2 equations. So we have to come up with another equation to solve them all. So what equation we can come up with? Generally speaking, the easiest one is regard to the dependent source. Since the dependent source value is in terms of one unknown, so we just think of this unknown. In this particular circuit, Ix is this unknown. And Ix is labeled here, this branch, downward current like this. So Ix itself equals to V1 minus 0 divided by 1 kilo ohm. So this is the third equation. So 1, 2, 3, 3 equations, 3 unknowns. We can find them all. And what we really care about is IT itself. It turned out to be 0.7 milliampere. And as we have discussed, the RTH just equals to the VT over IT, 10 over 7 kilo ohm. With this RTH, the corresponding Thevenin equivalent circuit is like this. As said, VTH is 0. And 0 voltage means short circuit, not open circuit. Be very careful on that too. Okay, so these two terminals are labeled given terminal A and B. This is the answer as Thevenin equivalent circuit. It's also interesting to think of Norton equivalent circuit. What does it look like? Exactly same. Okay, because current source now is 0, means open, parallel with this 10/7 and then feeding terminal A and B. You can tell this is nothing but the same circuit as Thevenin. This is a solution for example 3. Now let's continue to example 4. Find the Thevenin's and Norton's equivalent circuit across terminals A and B. This time A and B are here, kind of in the middle of the circuit. And also the problem is telling you keep two 1 kilo ohm resistors as circuit part B. It's nice. So defining these part as B, which cannot be touched. Well, these part left hand side of the two terminals as circuit part A, which gonna be replaced by Thevenin's or Norton's equivalent circuit. Okay, so we're gonna open terminal A and B's by removing part B to find out VTH, and then we're gonna find RTH according to the circuit scenario, which is clearly case 3. So we have both dependent and independent sources. So recalling the previous slide workflow here, to case 3, if you have both, we need to find the ISC, the short circuit current, and then find RTH by ratio between open circuit voltage and short circuit current. So how to find the short circuit current? We go back to step B here. So we need to replace the part B by short circuit. This time we are not simply open it, but we short it. And then find the short circuit current through that short circuit, which is the ISC. Okay? So let's start. So now we're seeing by opening the part B circuit, we end up with across terminal A and B here. So we are trying to find the open circuit voltage VOC, which is nothing but our VTH as before, KCL or KVL. I'm seeing two nice meshes, so I'm applying mesh this time. So first mesh here, rotating clockwise, we are coming across 3 voltage terms. One is the dependent voltage source with voltage value of 2K IX. We are coming across positive terminal due to the rotation direction first. So it's positive 2K IX. Then plus the voltage cross 1 kilo ohm introduced by mesh current I1. And then plus the voltage cross 2K, which is introduced by 2 current, mesh current I1 and I2. So 2K times I1 minus I2. Since I1 is downwards, I2 is upward through 2K. Okay. Sum them up equals 0. And in mesh 2, we have the same voltage cross 2K. However, because of the rotation direction, we are coming across negative terminal first. So it is negative 2K times I1 minus I2, or positive 2K times I2 minus I1. And then positive, negative 12 volts, we like it. It's very easy to deal with the voltage source in mesh and very easy to deal with the current source in Nodal. The last one is the voltage cross 2 kilo ohm introduced by mesh current I2. And it is very clear that IX here is nothing but I2, as our third equation. Or you can feel free to write I2 in terms of Ix directly, so that you don't need to have the third equation. So I1, I2, and Ix, three equations, three unknowns. So we can find all of them. However, we are looking for VOC, so we need to somehow link to this voltage. So how to do that? So by observing the circuit, VOC is nothing but the voltage across 2K with downwards current Ix. So very simple Ohm's law, we can find VOC. It turns out to be negative 6 volts. This is nothing but our VTH. So as the first step, find VTH. Second step, as we have discussed, we are looking for ISC so that we can find RTH as this. So instead of opening part B, we are shorting it, and ISC is a current flowing through it downwards. Okay, be very careful on this current direction. It has to be this way. So find out this ISC so we can find RTH. Let's see how to find ISC. Generally speaking, if we have short circuit, it's making the circuit tricky. So let's see here. Independent voltage source providing the current flow through the circuit. The current get out of the positive terminal, and somehow it's gonna try to go back to this negative terminal to have a closed loop. However, when the current trying to go back to the negative terminal, it's gonna reach this node from left, and then it's gonna choose either this path or this path. We encountered this scenario before, in where a short circuit is parallel with another branch. So we call it short this branch out, which means the current is always trying to flow through a path with minimum resistance, and the short circuit means zero resistance. That means no current gonna flow through this branch at all. All of them gonna flow through this short circuit back to the negative terminal of the independent source. With that being said, essentially we have this conclusion here. Ix is 0. No current flows through this branch at all. No current means open circuit. Also, meantime, due to the 0 Ix, the dependent source voltage value is 0 too. So 0 voltage means short circuit here. So here we go, is the resulted circuit we are going to find ISC from. Okay, this procedure is a little bit tricky, so slow down and try to digest and learn something out of it. And then how to find the ISC from this circuit? It's much easier, okay, because this is only one independent source feeding two parallel resistors, and ISC is nothing but the total current. So we can use Ohm's law. ISC equals to the voltage divided by the total resistance. However, be very careful. We need a negative sign because the independent voltage source providing a current this way, or say this way, which is opposite to the direction of the labeled ISC. So we have to have a negative sign in front of it. And at last, it turns out to be negative 18 milliampere. So after finding ISC, RTH equals to VOC divided by ISC. Turned out to be 1/3 kilo ohm. Now we have RTH and VTH. So the Thevenin equivalent circuit is like this. VTH series connected with RTH through terminal A and B, feeding part B. And here, VTH equals to negative 6 volts with this polarity, equivalent to positive 6 volts with opposite polarity. So this is the solution for example 4.